Alright guys, we are starting our probability unit today. We're actually going to do experimental and theoretical probability, and then we're also going to look at geometric probability. So we're kind of doing two lessons together since they kind of tie in very closely together. So probability of an event is a number from 0 to 1 or from 0% to 100% that describes how likely it is that an event will occur. Probabilities closer to 1 are more likely to occur, and probabilities closer to 0 are less likely to occur. Alright, you got a couple of vocab words here. Event, that's a single outcome or a group of outcomes. An outcome is the result of a single trial in a probability experiment. The complement of an event is all the possible outcomes that are not an event. An experimental probability, the ratio of the number of times an event happens to the number of times the experiment is done. All right, sample space, the set of all possible outcomes in a situation. And then theoretical probability, the ratio of favorable outcomes to the number of possible outcomes. So that's a little bit of vocab there to help yourself out. Here's, I guess, experimental and theoretical. In the format and how they write it here. So they'll say the probability of some event happening, and this is if it's experimental. You do the number of times the event happens over the number of trials. That's another word that I'll use for the number of times an experiment is done there. Right? Theoretical. So actually going back to experimental, that you actually go and test out. So like for example, if I was going to flip a coin or whatever, I'd say I flipped a coin 10 times. And I got 6 heads and 4 tails. That would be your experimental probability. The experimental probability of getting a heads was 6 because it happens 6 out of 10 times. Or the experimental probability of you getting a tails is 4 out of 10, or whatever that number is there. And usually we'll use those as decimals. We'll leave them as decimals, or you can write them as percentages. Now theoretical probability, that's the number of favorable outcomes versus the number of possible outcomes. So let's say, what are the odds that I flip a coin and I get a heads there? So there are 2 possible outcomes, but only 1 favorable outcome. So that'd come out as like 1 over 2 right there, and that'd be the theoretical probability versus the experimental, the one that you actually do. All right, and then the more times you do an experiment with your probability, the more times that happens, the closer it gets to your theoretical probability. We call that, I think, a normalizing. Okay, the sum of the probability of an event and the probability of its complement is 1. So that means the probability, if you take the sum of them, of something happening and something not happening, or I guess I should say, or something not happening, that should be 1. So your probabilities, if you added up all the different probabilities, it should be 1. So like for example, if we go back to the flipping the coins, the probability of flipping a heads is 1/2. The probability of flipping a tails is 1/2. If you add those together, that's 2 over 2, which equals 1. Right there. So let's go ahead and try out a few examples here. Some of them are experimental, some of them are theoretical. So look at this. Quality control inspector samples 500 LCD monitors and finds defects in 3 of them. What is the experimental probability that a monitor randomly selected has a defect? So out of the 500 he tested, 3 of them were defective right there. So we'll write that down, and then we'll simplify that down to like a decimal. So that'll come out is 0.006, I guess, when you do that. Or you could write that as a percentage. You could say 0.6% right there. All right, the reason that's useful is that we can predict how many should be theoretically defective if we had more than 500. Say we had 10,000. We could use that percentage to help us figure out how many of those should theoretically be defective. And that's kind of the whole point of it there. So next one here, park has 538 trees. You choose 40 at random and determine that 25 are maple trees. What's the experimental probability that tree chosen at random is a maple tree? And then how many trees in the park are likely to be maple trees there. So, okay, so essentially what we need to do is figure out the probability that there's a maple tree. So you're going to do the number of maple trees and then the number of trees over the number of trees inspected here. So we only checked 40 of them. We're not going to check all 538 of them because that'd take too long. So if we check a handful of them there, we can use that to make a pretty, good prediction, I guess, to figure out how many trees are truly maple trees, I guess. So they got this ratio here, 25 out of the 40 right there. If you want to simplify that down to a decimal, that'd be 0.625. Or you could even write that as 62 and then 0.5 percent right there of your trees would be those maple trees. Alright, so we punched that out. That's actually, I guess, kind of step 2 right here. They kind of have it broken down a little bit different than I think here. Just kind of do that. And then once you figure out that percentage, you can apply to the total amount of trees. And there's kind of, I guess, 2 different ways you can do this here. Some people are really comfortable with percentages. And if you want to do 62% of a number, you're going to move that decimal over twice, 0.625. And then you're just going to multiply that by the total number of trees, which was 538. And then if you punch that out, about 336.25 about are the maple trees. And this is all theoretical from here. That's not actually what we found there. So now another way some people do it is they like to change the 62.5. They like to write it as a proportion here. So they'll say 62.5 times or divided by 100, and then equals X trees over the total 538. And once you cross multiply and divide, you'll get the same thing. And I guess this part right up here, I guess I wrote it out again. I'm not really sure why that's there, but that's what we did there in step 3. Took the probability and then multiplied by the number of trees in the park. Okay, is the answer exact or an approximate? Even if it came out as a whole number, it's an approximate. That's because we're not actually sure, since we didn't go and hand count every maple tree, we're not actually sure how accurate that number truly is. So we use that so we don't. So that's so we don't have to go count. So that is, probability there in a nutshell. All right, what's the probability of rolling numbers that add to 7 when rolling 2 standard number cubes or dice? So you have 6 sides, right? Typically. So there's the possible numbers you could get there for one of the dice. And then the numbers you could get for the other dice. So you could have a combination of what we call snake eyes, 1, 1, 2, 1, 3, 1, all the way through. And we're trying to figure out which of them add to 7. So if you look here, they kind of already circled it for us here. These are the favorable outcomes right there. There are 1, 2, 3, 4, 5, 6 of those outcomes that add up to 7. So make a list. Okay, we kind of did that. Step 2, find the number of possible outcomes for the event. So since there are 6 times 6 options there, that would get us 36. So 36 total outcomes, but then there are only 6 of the favorable outcomes. So we'll say the 6 favorable over the 36 total. That reduces to 1/6. Or you could write that as a decimal, and that'll be about 0.16 repeating, or you could say about 16.7%. And just depending on your teacher, check with them to figure out how they want the format of it. Okay, look at this. What is the probability of getting a sum of 13 when rolling 2 standard number cubes? So, or 2 dice. So I'm going to look through here and see if any of those options add up to 13. Now, the biggest option right there would be 6, 6, but that would only add up to 12. there. So that doesn't even get it for us there. So actually there are no favorable outcomes. So we say 0 and then added 36 total outcomes. So it comes out as 0, or you could say even 0% right there. So there is no chance of that happening. That will not happen if you are rolling standard dice. Okay, let's see what this next one here. A jar contains 10 red marbles, 8 green marbles, 5 blue marbles, and 6 white marbles. What is the probability that a randomly selected marble is not green? Okay, so we need to think about the favorable, or what we want to happen, over the total number of outcomes. Okay, so there are, first of all, we need to figure out the total number of, I guess, of these marbles here. So you got 10, 8, 5, and 6. So I believe that'll be 29. So there are 29 total marbles that you can pull. So then the probability that they are not green. So we need to look at all of the ones that are not green. So you have 10, you have 5, and then you have 6 right there. So that is 21 total that are not green. So we call that our favorable right there. So that's your probability. 21 out of the 29 marbles are not. That's about 0.724, or you could say about 72 and then 0.4%. Now where probability gets really fun is when you start adding in other factors. Maybe you pull out multiple marbles at the same time. Maybe you pull out one at a time. Maybe you pull out one at a time without replacing or with replacing. That's when probability gets pretty advanced there, but we stick to it. Pretty simple today.